Hi friends, I am Dr. S. KUMARESAN, Associate Professor of Physics. Today we are going to discuss about Hall effect. First we have to define what is Hall effect. When a magnetic field is applied perpendicular to the current carrying material, the material may be a conductor or semiconductor. There is a voltage developed across the specimen such that the developed voltage is perpendicular to both current and magnetic field. This phenomenon is called Hall effect and the developed voltage is called Hall voltage. Okay, first we see what is Hall effect. Let's see Hall effect in detail. Hall effect was discovered by scientist Edwin Hall in the year 1879. Conductivity measurements do not give sufficient information about the charge carriers, and also we cannot easily calculate the mobility of the charge carrier. In the case of semiconductor, there are two types of semiconductor, p-type semiconductor and n-type semiconductor. In the case of n-type semiconductor, the majority current conduction by electrons and minority charge carriers are holes. In the case of p-type semiconductor, the majority charge carriers are holes and minority charge carriers are electrons. So, which one contribute the current conduction in the case of semiconductor, and also to know or identify the type of semiconductor, Hall effect help us to easily identify the type of semiconductor. Yes, material, if it is a semiconductor, n-type semiconductor as shown in figure, and here current is along x direction and magnetic field is along the z direction, then the voltage will be developed along y direction. So, when the magnetic field is applied perpendicular to the current carrying conductor, what happens? There is a voltage developed across the specimen. Each charge carrier in the material experience two forces. One is the force due to electric field. One is the force due to electric field, let it be Fe, and it is given by minus Ee. And another one is force due to magnetic field, that is Fm, and this is equal to minus Bev, since the velocity is along x direction and the magnetic field is along z direction and the field is along y direction. In equilibrium condition, these forces are balanced, so we can write minus Ee is equal to minus Bevx, okay, and it will be cancel out. So, simplify this equation, we have the Hall field Ey is equal to Bz Vx. Let it be, this is equation 1. We know that the current density Jx along the x direction is equal to charge carrier is minus n and with E, and here with velocity x. From this we know that what is the velocity, this is equal to Vx is equal to Jx divided by Ne with negative sign. This is equation number 2. Now substitute equation 2 in 1, we get the Hall field Ey is equal to Bz minus Jx divided by Ne, or Ey Hall field is equal to minus Jx Bz divided by Ne. This is equation 3. In the equation 3, the term 1 by Ne minus 1 by Ne is a constant. 1 by n is a constant, and it is called Hall coefficient. This is called Hall coefficient, and let it be represented by the letter RH. Hence, equation 3 becomes, hence, equation 3 becomes the Hall field Ey is equal to what? That is R, H, and then J, X, B, Z. This is equation number 4, and it's the expression for, equation 4 is expression for Hall electric field, and this Hall coefficient gives the sign of the charge carrier. Here it's a n-type semiconductor, so the majority charge carrier is electrons, hence the Hall coefficient is negative sign. In the case of p-type semiconductor, the charge carrier, majority charge carriers are holes, so it would be become a positive one. So by knowing Hall electric field, easily we can know about. Equation 4 is the expression for Hall electric field. From Hall electric field, you can know about the type of charge carrier. For n-type charge carrier, we know that the Hall coefficient is -1. In the case of p-type semiconductor, the Hall coefficient must be +1. Yes. From Hall electric field expression, we can find the Hall voltage is depends the current, strength of the current, and also it depends the strength of applied magnetic field, but it is inversely proportional to the thickness of the material. Now we see what are the applications of Hall effect. The Hall effect help us to identify the type of semiconductor, if it is a semiconductor p-type or n-type. Now we see what are the important application of Hall effect. The most important application of Hall effect is sign of the charge carrier, sign of charge carrier, and second one is the carrier concentration. Carrier concentration. We know that what is carrier concentration? Number of charge carriers available per unit volume. So the charge carrier concentration N. And third one, mobility of charge carrier. Mobility of the charge carrier. So mobility of the charge carrier can be measured directly. And fourth one is type of semiconductor. Type of semiconductor. P-type or N-type. And fifth one, in magnetic sensor. In the case of magnetic sensors, it play very important role. Thank you.